hope for all of you that you remain with power. I should say to that kind of end, you're always welcome to come to class in person, unless I'm not in person. I will always plan on being in person unless I can't be for some reason. I will certainly communicate about that if I'm not going to be. But you're also always welcome to come virtually. You're also always welcome to just watch the video later. So you can come however you want. To that end, though, whichever way you come, whether it's in person, virtually live, or watching the video later, I need you to fill out the attendance form, because that's how we keep track of student usage. And that's really all it's for this quarter. I know last quarter, like some of you were taking code 21A and you were getting a pass, no pass grade for it. Some of you weren't. Some of you don't know who I am. This is the first time you've ever seen me. And you really needed to fill out the attendance form last quarter to pass the class. That is not true this quarter. You could do none of it and be fine because it's not for a grade. But I need you to do it so that we can record your attendance. So for those of you in class, you can scan that QR. And if also it's not the one I've been using in the past, it's just the generic AATC QR code. So you can scan it there or there. I recommend bookmarking it on your phone and just marking your attendance every time you come to class or come to class on Canvas. And here is the attendance form link if you would like it for those of you on Canvas. On Zoom, Canvas. And yeah, so if you're fill it out now, or if you watch this video later, fill it out then. Is the one what? Yeah. The links on Canvas should be the same as the ones in this room. And it's very generic. It'll just ask you if you're attending in person or virtually, and it'll ask you what class for. And there should be James 21B workshop or whatever it says. That should be an option on there. So that's kind of probably the most important detail I can think of is please fill out the attendance form. I'll remind you the first few times, but just get in the habit of doing it whenever you come, and that'll be great. And if you forget once or twice, it's not the end of the world. What else? What else did I think was important? Let's take a look at Canvas for a second, just so you can see what is on there for you. So here's the home page, which redirects to the syllabus for now. I might change it so it redirects to the modules, because I think the modules are probably where all the most important information is. But just a few things to see on the home page. You'll see the most recent announcements. I did ask that everyone on this first announcement, I think, yeah, a lot of you have done it, some of you have not yet. Just put in who your 21B teacher is. So when you have a chance to do that, it's not like vital. I just want to know kind of if there's someone I can ignore. Like if none of you are taking Kapovich's class, then I won't bother looking at his whatever he's got going on. So that's just kind of from my own personal knowledge. Back to the syllabus, let's see. And then here's all the usual information, where class is, how you can get a hold of me, when and where my office hours are. That's always the easiest place to find it. And then about this class, blah, 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 blah. Just trying to think. I mean, there's mildly important information here, but really this class is you come, we talk about math, you go do more math other places, right? Like there's not a lot of like, I'm not collecting homework, I'm not assigning anything. There's no real details to this class other than what's the one thing you need to do? Fill out the attendance form every time you come to class. Thank you. What else? Let's just scroll down here to make sure I'm not missing it. Also, for those of you on Zoom, please feel free to unmute yourself if you want to say words out loud, or you can always use the chat, is probably preferable. But if you're using the chat and I don't see it, you can unmute yourself and scare me to death and say words. I'll probably like, well, let's see. Accommodations. If you need some sort of accommodation, please let me know. Again, there's not a lot of test taking or assignments or things that usually require accommodations, but that doesn't mean there couldn't be. So if there's something like things are already going to be recorded. If you need something, let me know. I'm always really happy to try and accommodate in whatever way I need to. I imagine the Zoom instructions don't need to be read because you've all used Zoom so many times at this point. Do the attendance. If you miss class, that's totally fine. You can always watch the video recording. You can either find it on YouTube or I will post them all on Canvas as well. I'll post the class notes as well, which I'll try to write nicely. Come on in, have a seat. And then places you can get more math help, my office hours, grants website, the AATC website. There's another website I should put on too for Kuba. He's good. So yeah, there's the syllabus. You should take a look at it. But again, it's pretty much it's the same thing we're doing last quarter. We're just here to talk about math. If you have questions, if there are things you really want me to cover, letting me know before class sometime is good. Like if you have a specific question, it's totally fine. I'm happy to look at specific questions. They can be homework questions. I'm kind of the opinion that pretty much any homework problem you might be asked, the answer is probably findable somewhere. So it's not like a crime for me to go over it in class. So if you have specific homework questions or generic homework questions, I'm happy to go over them. What else? Oh, for those of you that just walked in, and I'll say this many times this first couple weeks, please do fill out the attendance form. You can find it by scanning that QR code or that QR code, and you'll fill it out and you'll click on James 21B. Is this a workshop or co-class? It says co-class. You'll click on that one, James 21B co-class. Let's see. So syllabus, yeah, it's just fine. Let's look at the modules because that's probably where I would imagine most of you will eventually end up being most of the time in this Canvas. There's some useful links. You can find the Zoom link there. You can find the class attendance form link there. I recommend bookmarking it. You can find the 21B playlist if you want to go to YouTube specifically. This also has my videos from years past, if we get there eventually. So you can find, oh yeah, there's Bearded James over there. You can find all sorts of videos from when the pandemic started. So good times. Yeah, yeah, they really do go back. Okay. Or forward. Sorry, they go back to as far back as October of 2020. So if you want to see some old, I mean, it's going to be a lot of the same stuff. So I will also post the new videos there. But it'll probably be easier for you to find the class videos if you want to find them down here where they will start getting posted once there are class videos from this quarter to post. There's some handouts, derivative worksheet, and the answers, which I gave an announcement about. There's also a link to the class notes. So I will post the class notes that I write here as well if you want to look at them again. Grant's website again. Grant's got a great website. It's got lots of useful information. And then here is actually a link that I'd kind of forgotten about. This has some videos that we made kind of at the beginning of 2020-ish that have just videos on various topics from 21B. And it's not just me, it's various math specialists. So if you scroll down here, they take a moment to load, but you will maybe sometime they actually do start to fill in, but they do take a minute. Oh, there you go. You can kind of see maybe one, I don't know. There are videos here, I promise. It's not just a lie. There we go. There's Grant doing a video on antiderivatives. There's Grant doing a video on some more antiderivatives. So there's all kinds of extra resources and materials if you're looking for that kind of stuff. But really, I mean, most of this is just, we're going to talk about whatever topics we think we need to talk about. I'm planning on talking about antiderivatives today because that's usually where things start off. So the plan today is to talk about antiderivatives and probably on Wednesday to move into talking about Riemann sums and that kind of stuff. So usually the way this class goes is first we talk about what an antiderivative is, very kind of basically, and then we talk about Riemann sums and defining the integral, and then kind of getting back to how the integral and the antiderivative are connected to each other. That's usually the way people do it. Not everyone does it the same way though. So questions so far about any of the oh gosh, I never think of the word I'm looking for that. Any of the basics of class, the rules, regulations, I don't know. There's a word I'm trying to find. Thank you, yeah, the logistics of class. It's not quite it, but it's close enough. There's not a lot of logistics. What else? By the way, in case you have not met me before, this is your first time, my name is James. My name is James Parmenter. You can just call me James. It's really fine. You can also, if you don't like calling a teacher by their first name, I totally understand. You can call me Mr. Parmenter, which is kind of a mouthful, but it's not too bad. But I like my first name a lot. It's pretty great. I'm a fan of James. It's a good name. I've always thought. I graduated from UC Davis many, many years ago in 2000 and what year did I graduate? 2003. Yeah, I was a student from 1998 to 2003. I graduated in math. It was a perfectly fine major. I don't particularly recommend it, but still. That's a little bit about me. I live in Woodland, and I'm from Arcata, California, if you've ever heard of it. It's where the new Cal Poly is. Or Humboldt State, sorry, what I will always think of as a Humboldt State University, but which I guess now is Cal Poly Humboldt. Sounds weird to say, is located. It's a nice place to grow up, but I probably wouldn't want to live there. All right, let's talk about antiderivatives. Let's see if my handwriting has improved at all. Let's see, I'm trying to think if there's anything else I need to say. I don't think so. Oh, cool, yeah. Yeah, I'm happy to, for those of you on Zoom, I see that the link, the live transcription, closed captioning has been enabled. I'm always happy to do that. I don't think there's anything I actually have to do. I think it just happens if someone requests it to happen, so feel free. Sometimes it weirdly like pops up, I can see the transcript, and then it's kind of like, oh, I can see the words I'm saying. It's not good. It's a little distracting. All right, antiderivatives. Antiderivatives are kind of exactly what they sound like they are. Meaning they are the function that is, if you have a function, you want an antiderivative, the antiderivative is just the thing that if you take the derivative of that, you get back to the function you started with. So kind of a common first example is maybe my function is 4x cubed. And there's kind of two, well, it's kind of annoying at first, and we're going to get rid of it real quickly. But there's a couple ways people write antiderivatives before we develop the usual notation. So the typical antiderivative notation would be, I see how terrible this is already. We would use a capital F of x to be, well, whose function has a derivative that's 4x cubed? X to the fourth. Because the derivative of x to the fourth is 4x cubed. So that's always the logic there behind what an antiderivative is. It's because the derivative of x to the fourth is equal to 4x cubed. Now, as you might observe, that's not the only antiderivative. This f of x equal to x to the fourth plus 6 is also an antiderivative because the derivative of 6 is 0. So typically we say the most general antiderivative of capital F of x equal to, 4x to the third, apologize, x to the fourth plus c. So we typically just tack on a plus c for any constant, and that's the general antiderivative. So that's one way of writing it. The other way people often do it is they say they're going to give you, they're going to call the thing you're starting with the derivative of your function. So they say, given g prime of x equal to, I don't know, x to the sixth, what's g of x equal to? Well, g of x is the antiderivative of g prime of x because the derivative of g of x is g prime of x. So, what's the antiderivative of x to the sixth? Write it down. See if you can think about what it might be. I'm going to take a guess. But that guess is wrong. X to the seventh is not the antiderivative because if that were my antiderivative, the derivative of x to the seventh is 7x to the sixth. We're off by a multiple of 7. And that's going to happen a lot. And typically, whenever you're off by a constant multiple, you can adjust for that really easily by dividing by that constant or multiplying by its reciprocal, however you want to say it. So people will often write this as 1/7 x to the seventh, or they might write it as x to the seventh over 7. Either way is fine. I'm kind of a fan of the second way, but whatever. Excuse me. So as you might already be feeling, at least I'm feeling, this notation is annoying. Right? I don't want to write the function is this, the antiderivative is this 10 times. Like it's terrible. So what we're going to do instead is we're going to use the notation that we know that we're going to end up using eventually anyway. and just kind of pretend like none of the meaning is there yet. So we're going to say that the antiderivative of x to the 6th power dx is equal to x to the 7th over 7 plus c. And for now, all we're going to do is just pretend like there's no other integral meaning here and say, we know that this symbol means find the antiderivative. And then later on, we'll actually talk about the connection of what the integral is, and the antiderivative, and the fundamental theorem of calculus, and all that stuff. But for now, when we're just talking about antiderivatives, we want this notation just to make our lives easier. And then in general, we have what I like to call the anti-power rule. So if you're going to take the antiderivative of any power of x with respect to x, that's what that little dx is for. It's telling you what variable you're anti-differentiating with respect to. Well, it's going to be the same as this. Here we added 1 to the power and divided by the new power. We're going to do the same thing here. We're going to add 1 to the power, divide by the new power. And of course, we're always throwing on a plus c. This is probably the antiderivative rule you will use the most ever because it just comes up all the time. You take the antiderivative of x squared, x cubed, so on, so on, so on. Now I should leave myself a little bit of space because there's one value of p that's not going to work for. What's the problem here? If you have a p plus 1 in the denominator, you don't want p to equal what? Well, we don't want the denominator to equal 0, which means we don't want p to equal -1. So we can't use the power rule to anti-differentiate x to the -1. So while we certainly know that the integral of x squared is x cubed over, so I will accidentally say integral because they're the same thing. And then most people said, I'll try to say antiderivative for now. But if I say integral, just pretend like I said antiderivative. When we take the antiderivative of x squared, we get x cubed over 3. But when we take the antiderivative of x to the negative first, you don't get x to the 0 over 0. That's a problem. But if you think of it or rewrite it as the antiderivative of 1 over x, you might remember a function whose derivative is equal to 1 over x. You might not. I know it's been 4 weeks. It is the natural log of x. Now, there's something kind of interesting here. I'm gonna hold off and write that down for just a second until I do this first. Let's find the derivative of the natural log of not x, but the absolute value of x. Because that's what's going to be our answer. Let's see here. So absolute value. Absolute value is always kind of it's not very fun. Absolute value is a little bit frustrating because it's really a piecewise function. It's equal to x when x is positive. It's equal to -x when x is negative. So what we can actually do here is say this is equal to the derivative of a piecewise function. It's the derivative of the natural log of just good old x if x is already positive. But if x is negative, then the absolute value of x is -x. Right? So if x is like -5, then you get -5, which is +5. And you can take the natural log of 5 and get some weird number, like 1.61, I think. So what's the derivative of the natural log of x? We know this. You guys told me already. It's 1 over x if x is positive. Okay, but now, chain rule, the derivative of the natural log of some stuff is 1 over the stuff times what? Right. Or more generally, the derivative of the stuff. But those are the same. 1 over -x times -1 is 1 over x. So whether x is negative or x is positive, the derivative of the natural log of the absolute value of x is equal to 1 over x all the time. So here's what that means for us. It actually means, and this is kind of important, it comes up all the time. When you find the antiderivative of 1 over x, I wouldn't say it's incorrect to say it's the natural log of x. It's just not as correct as it could be. It is more correct, it is correct to say it's the natural log of the absolute value of x. So that's something to be aware of. When you anti-differentiate 1 over x, you get the natural log of the absolute value of x. Kind of cool. It's really just a domain issue. We want our antiderivatives and our functions to have kind of the same domain if they can. And 1 over x is a domain of everything except for 0. So we'd like its antiderivative to have a domain that's also everything except for 0. And now it does. Kind of cool. Yeah, question.
So when you differentiate x and you put it into these functions, having a little hard time negative x when x is negative turns into a positive, but why are we considering that for?
So sorry, say that one more time.
Why are we considering negative x when the domain of the absolute value is only positive?
Well, because I'm writing the natural log of the absolute value of x, right? So absolute value of x is always positive or technically non-negative, right? But whatever. So this is always positive. So if x is positive, then the absolute value of x is just x. Whereas if x is negative, then the absolute value of x is negative x.
Sure, which turns into a positive.
Right.
But why are we having the absolute value in the first place?
Because I know it's the answer to the question. So I'm aware of the fact that that the derivative of the natural log of the absolute value of x is 1 over x. Right, but the difference between the natural log of x versus the natural log of the absolute value of x is this function has a domain that is everything that's positive. And this function has a domain that is everything except for 0. And if we have a choice, we would prefer to pick the function that has a larger domain. We prefer to pick a function that has the same domain as the function it's the antiderivative of. That's why. Yeah, cool. So it's really, really important to be aware of kind of how to anti-differentiate lots of things you already kind of know. I know that sounds kind of circular, but it's not. Let's look at a couple of examples. What about the antiderivative of, say, cosine of x? Do we know a function whose derivative is cosine? I think we do. Yeah. Sine plus c. And this, I mean, so no, we should write them all down. There's a lot to write down, but we're going to write them down because I think it's a good starting place. So what about the antiderivative of sine? Is it negative cosine? Yes, it is. Now you could, for each of these, write down on the side because the derivative of sine of x is equal to cosine of x, or because the derivative of negative cosine of x is equal to positive sine of x. It's kind of implied though every time, right? When you're saying the antiderivative of cosine is equal to sine, the exact reason is because the derivative of sine is equal to cosine. There's this kind of very natural relationship between a function and its antiderivative. And if you take the derivative of that, you get back to the function. I kind of like to think of it as being similar to inverse functions. Derivatives and antiderivatives are operations that undo what the other one does. Just like inverse functions are functions that undo what the other one does. So if you take a function and you take its antiderivative and then take its derivative, you should always get back to where you started. I want to mention if you start with the antiderivative and you differentiate and then anti-differentiate, you don't exactly get back to where you started because you could be different by a constant, but we don't worry about that too much. Yeah, let's list out all the functions, not all of them. I mean, like a majority of the functions you are expected to kind of know the antiderivatives of because you know how to differentiate. So let's work through the trig ones. So how about the antiderivative of secant squared? let's see, derivative of tangent of x is equal to secant squared of x. So the antiderivative of secant squared of x is equal to tangent x. And the antiderivative of cosecant squared is going to be negative cotangent of x plus c. And the way I remember it is the co-functions, cosine, cotangent, and cosecant all have negative derivatives. So when we take their antiderivatives, we have to be a little bit more careful. Whereas the non-co-functions, secant, tangent, and sine, those ones are usually a little more straightforward with the plus or minusness. Let's look at the last two trig functions we know, or I really should say functions we know that are derivatives of trig functions. So let's see. What's the derivative of secant? Exactly, secant times tangent. So if we know that the derivative of secant is secant times tangent, then we also know that the antiderivative of secant times tangent is equal to secant of x plus c. Definitely get in the habit of writing plus c. And then in a similar way, the antiderivative of cosecant of x times cotangent of x is going to be cosecant of x, except it's going to be negative cosecant of x. Because the derivative of cosecant of x is equal to negative cosecant of x times cotangent of x. And these are all the trig antiderivatives we are expected to know at this point, just because we already know these derivatives. So any derivative you know the reverse antiderivative. So let's see. We've got the trig ones we know. There's a couple we're going to learn later. Eventually, we will learn what the antiderivative of tangent is and the antiderivative of secant and cotangent and cosecant, but that's for later. We talked about natural, or the antiderivative of 1 over x, that's natural log. What other functions have we not talked about yet? I can think of one. Everyone's favorite one is power. Well, we talked about powers. There's a different word you're looking for, I think. Exponentials, right? Exponentials. What's the antiderivative of e to the x? Oh, it's the best one ever. It's e to the x. Kind of great. Yeah, kind of it. Well, it's not all there is to. How much time we got? We got time. Okay. Let's see. I had some notes here. I just so I could look back at my notes for a second here just to make sure I'm covering all. Oh yeah. There is one other class I wanted to mention, but we'll get there in a second. Yeah, let's do that. Let's sure. Let's talk about a few more, and then we'll talk about the thing I really want to talk about. So, what about the integral of 1 over x squared? Integral antiderivative of 1 over x squared plus 1. Yeah. So this is one that, although there are methods you can learn later, this is a derivative you're kind of expected to recognize. The antiderivative of 1 over x squared plus 1 is the arctangent of x, or if you prefer, the inverse tangent of x. Either way you want to write it. Plus c. And to that end, the antiderivative of 1 over the square root of 1 minus x squared is also an inverse trig function. It's the arc sine of x, or the inverse sine of x. And lastly, and this one comes up less often, the integral, the antiderivative of 1 over x times the square root of x squared minus 1. This one is always a little funky, which is why people mostly avoid it. It's typically going to be written as the arc secant of the absolute value of x plus c, or the inverse secant of the absolute value of x plus c. I don't want to get too into this one because it's a little funky, but there are reasons for absolute values here that require lots of explanation, and actually people making a literal choice about how they want to define the function. So usually your teacher will just kind of gloss over and be like, we're not really going to talk about that one very much, but if it does come up, that's what it is. Unless unless your teacher says it's something different. There might not be an absolute value when your teacher talks about it, but they probably won't even talk about it, so don't worry about it too much. So those are fine. What happens if we start like multiplying by stuff? Like what if I instead wanted to find, I don't know, the antiderivative of 6 over x squared plus 1 plus 5 e to the x minus 4 sine of x. Well, constant multiples are not really a problem. Although you certainly could write this out as many antiderivatives added or subtracted together. You don't really need to. So even I'm going to write out the steps, but really I would say you want to skip to the end here. That 6 is just a multiple. The antiderivative of 6 over x squared plus 1 is going to be 6 times the arctangent of x. The antiderivative of 5e to the x is going to be 5e to the x. The antiderivative of negative 4 sine of x is going to be negative 4 times negative cosine of x, which I really should write as positive 4 cosine of x, but I wasn't paying attention. So this is going to be equal to 6 arctangent of x plus 5e to the x plus 4 cosine of x. Constant multiples just kind of hang out. If you had wanted to, you could have done the work of writing this as 6 times the antiderivative of 1 over x squared plus 1 dx plus 5 times the antiderivative of e to the x dx minus 4 times the antiderivative of sine of x dx. No one expects or wants you to do that, really, unless they specifically say they want you to do that, which occasionally someone's like, do all this work to see that things work. It's a lot like derivatives, right? When you took the derivative of many things, added or subtracted together, you just did each one and added or subtracted the results together. And the same deal with constant multiples. When you took the derivative of something that was a constant multiple times a function, that constant multiple just stuck around. Same deal is true for antiderivatives, which is nice. Yeah, let's get to the point. So, not the point restaurant. Okay, phone. What about the antiderivative of e to the 6x? What function is a derivative that is e to the 6x? Well, it might be e to the 6x-ish. E to the 6x, well, plus c. Let's check. If I take the derivative of e to the 6x, when I check, by the way, I'm never going to write the plus c when I check because I know the derivative of c is 0. But just in case you're wondering why I'm not writing it, that's why I'm not writing it. The derivative of e to the 6x is e to the 6x times 6. That's not what we wanted. We wanted e to the 6x. Luckily, we already kind of know how to adjust for a constant multiple, right? Just like when we were doing the antiderivative of x to the 6th, and I said it was x to the 7th, but then we were off by a multiple of 7, and we divided by 7. The same kind of thing is true here. If the antiderivative of e to the 6x, if its derivative is off by a multiple of 6, well, we're going to divide both sides by 6. So what I really need here is a 1/6. So I can put a 1/6 there and a 1/6 there. And then those 6's cancel out, which is great. And this is a very common thing to happen. If you're off by a constant multiple, you typically just end up dividing by that multiple. So looking at some other examples here. Sorry, papers. Yes. Cool. What if I wanted to find, say, the antiderivative of secant of 5x times tangent of 5x? Well, we know the antiderivative of secant of x times tangent of x is secant of x. So I'm pretty sure this is going to be secant of 5x-ish. But I know when I differentiate this, what constant we're going to end up multiplying by when we differentiate secant of 5x. Everybody, show me on your fingers. This one. Yeah, right. We're going to multiply by 5, but we don't have a 5 here. So we need to divide by 5 to account for the 5 we were going to end up multiplying by. Questions about this? This is, even though we haven't talked about U substitution yet, and we're not going to for a while, this is commonly referred to by myself and Grant and anyone that works at the AATC as a mini U substitution, because it's kind of like a very small thing that we end up just saying, you don't really need to do that U sub. You can just kind of get away with knowing how this works. And it works this way kind of for any constant multiple of x. So for example, if I was anti-differentiating cosine of 4x, I know the antiderivative of cosine of x is sine of x. So the antiderivative of cosine of 4x is sine of 4x, but then I need to divide by the coefficient of x. Or if you prefer, 1/4 sine of 4x. Let's see. Totally works. If you need to go, you're welcome to go. Yeah. Yeah. In general, if you need to leave early or come late, that's totally fine. You don't need to like say words or anything. Be like, I'm taking off. See it. Yeah, why don't you all try this one? Find the antiderivative of secant squared of 3x. Try that one. Let's see. So when I look at this, I kind of ignore what's inside the function for a second. Like I'm really just looking at secant squared of blah. And I know that the antiderivative of secant squared of x is really what I'm thinking, is tangent of x. So then I'm thinking, well, it's tangent of the same stuff, but then I have to divide by the coefficient of x. Or really, no, I shouldn't say that. I'm really thinking specifically the coefficient of x here because it's just a multiple of x. What I should point out is this only really works if it's just like a multiple of x. For example, if I asked you an impossible question, because it literally doesn't have an answer, if I asked you what the antiderivative of cosine of x squared is, it would be incorrect because again, there is no answer to this question, which is kind of disappointing. It would be incorrect to say that this was sine of x squared divided by 2x. The reason being is here, if I differentiate this, I'm not just taking the derivative of sine of x squared and getting cosine of x squared times 2x and then dividing by this thing here, because that's not the constant. It's a function. It's a variable. I have to use the quotient rule here if I'm going to actually differentiate this. And it's a lot worse, right? The derivative of sine of x squared over 2x is bottom derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That is definitely not equal to cosine of x squared. Whereas that problem doesn't pop up here because tangent of 3x divided by 3, dividing by a constant doesn't necessitate the quotient rule, right? Dividing by a constant is really just multiplying by the reciprocal. And so you can just leave that out in front. So totally works if you have a multiple of x. It does not work if you have other functions of x. Well, at least not if you just have that. On the other hand, I should say you could definitely find the antiderivative of 2x times cosine of x squared. Let's see. I'm trying to find a function whose derivative is cosine of x squared times 2x. Well, what's a good guess? Probably not cosine, but sine. So if I think about sine of x squared, does that work? Let's see. Derivative of sine of x, let's check. The derivative of sine of some stuff is cosine of that stuff times the derivative of the inside. Yeah, that totally works. So sometimes you can kind of just figure it out by saying, well, this inside stuff, its derivative looks like it's right there. So it's probably going to work out to just kind of ignore it, in other words. Let me ask you all to try a similar problem. Try finding not that one. I don't like that. Sure, why not? Fine. Try finding the antiderivative of 3x squared times e to the x cubed. And check your work by differentiating your answer. All right, I have a guess. I think it's e to the x cubed plus c. I forgot my plus c up here. So let's see, the derivative of e to the x cubed is e to the stuff times the derivative of the stuff. Yeah, that checks out. What if I had asked instead, what if I made it a little bit harder and said, what's the antiderivative of just x squared times e to the x cubed? What's the only difference between this first one I asked and this next one I asked? There's no multiple of 3. So if I'm just changing my answer by a multiple of 3, this answer or this answer is really just going to be this answer, excuse me, divided by 3. So this should really just end up being 1/3 e to the x cubed plus c. And it is. So the derivative would be e to the x cubed times 3x squared times 1/3. And the 1/3 and the 3 we cancel out. So what I'm trying to hopefully get you to see is that constant multiples don't really matter. Like they matter in that you need to be careful about them, but you can always kind of fix it if it's off by a multiple that's constant. Yeah, a couple of examples I have in mind here. So a few things to be aware of. If you're anti-differentiating something like x to the 5th over 2, that 2 is inconsequential. Like it, okay, it's not like not meaningful, but it doesn't really matter. I'm thinking of this as 1/2 times the antiderivative of x to the 5th. In fact, you'll probably hear your instructor and myself say a lot, pull out your constant multiples, pull them out in front of your antiderivative and then deal with them at the end. So then the antiderivative of x to the 5th is x to the 6th over 6. And then we can multiply those together and get x to the 6th over 12. Sure. Why don't you try, where'd you go? I had one. Try these two. Try the integral, sorry, the antiderivative of 4 over x to the 6th, which you might want to rewrite before you antidifferentiate. And then after you do that one, you can try this next one. Negative powers can be tricky. The anti-power rule always works the same way, whether the power is negative, positive, or something else terrible. So we're always adding 1 to the power and then dividing by the new power. So here we're going to get 4 times x to the -6 plus 1 is -5 divided by -5 plus c. And you can totally leave it like this, but some people are going to rewrite this and rewrite it as -4 over 5x to the 5th because they want to, because they like a positive power. Don't let that throw you though. It's still the same as this. Same kind of deal here. For 1 over 9x cubed, I brought out the 1/9. I changed the 1 over x cubed to x to the -3rd. And now to anti-differentiate that, we're going to add 1 to the power. So we're going to negative 3 plus 1 divided by the same thing, which you probably don't need to write out, but it's good to write out sometimes. Negative 3 plus 1 is negative 2. So I have 1/9 times x to the negative 2 over negative 2. I'm going to multiply those denominators together and get a negative x to the negative 2 over 18. Or preferably, in my opinion, and that's just my opinion, a negative 1 over 18x squared. Only because I've been, I don't know, brainwashed to think that you should always have a positive power if you can. It's not really true. You don't need to have a positive power necessarily. I just like to. There was something there that I wanted to mention. Oh yeah. So let's look at 1 or 2 more examples, and then there's one other thing I wanted to say. Fine. Let's look at this example. The antiderivative of the 7th root of x to the 5th plus 6x cubed minus 5x to the just 5x over 2x squared. And that looks real hideous. Fine. There is no anti-quotient rule. There is actually kind of an anti-product rule, which we'll talk about much later. But quotient rule, can't really deal with. So what we're going to do here is we're just going to simplify. And that's often when you're trying to find an antiderivative, your first method of attack, if you can't just see what the answer is right away, is to try and simplify the thing you're anti-differentiating. So I'm going to rewrite all these as powers of x. So 7th root of x to the 5th is x to the 5/7 over 2x squared. I'm going to just divide each thing by the 2x squared. And then I'm going to simplify each of them, right? So what I can't do here is just anti-differentiate the top and the bottom separately. I have to simplify it just down to a power of x, because it's kind of the only thing I know how to do. So let's see, 5/7 minus 2 is negative 3/7. Oh no, sorry. 5/7 minus 14/7 is negative 9/7. That's terrible. So it's x to the negative 9/7 divided by 2. And this one's a little nicer. This is just 3x. That's much better. And this is minus 5/2 x to the negative first. Sure. Yeah, I don't love that gross fraction, but it's fine. Even though it's ugly, it still works the same way, right? We're just going to subtract 1 from the power. Sorry, not subtract 1 from the power. That's differentiating. We're going to add 1 to the power and divide by the new power. So this first term here, I'm going to put the 1/2 out in front, and then the antiderivative of x to the negative 9/7 is going to be x to the negative 9/7 plus 1 divided by negative 9/7 plus 1. I know we can probably do that math in our head, but if you can't, it's always fine to just write it down, right? I don't want to think about what negative 9/7 plus 1 is. I'm just going to write it down like that, and then I'll fix it in the next step. Let's see, plus 3x squared over 2 minus, okay, here I have to be extra careful. X to the negative 1, I can't add 1 and divide by the new power because it'd be divided by 0. That x to the negative 1's antiderivative is the natural log of the absolute value of x plus c. And then I would do a little bit of simplifying. Negative 9/7 plus 1 is negative 9/7 plus 7/7, which is negative 2/7. So I'm going to have 1/2 times x to the negative 2/7 over negative 2/7. That's also terrible still. Plus 3/2 x squared minus 5/2 natural log of the absolute value of x. And then I guess I would fix this and write it as 1/2 times 7/2 is 7/4, so negative 7/4 times x to the negative 2/7 plus 3/2 x squared minus 5/2 natural log of the absolute value of x. It's not pretty, but usually the answers aren't very pretty in this class. So it's good to get used to the answers being kind of not nice, because they're often going to be not very nice. All right, it's 2 o'clock. I should stop saying words. Yeah, I will post the video to YouTube and Canvas. I'll post the notes as well. See you all on Wednesday. there's a possibility of me canceling class on Friday because I might go visit my brother on Friday. I probably am not going to because of the weather. But if I do cancel class on Friday, I will post in Canvas to let you know. If you don't hear anything in Canvas or via email, you should assume the class is happening on Friday.